In this video, we're going to look at an application of linear functions, which is linear inequalities. And basically, this is what happens when you take out the equal sign in a linear equation and replace it with any of the four inequality symbols. These look very similar to linear equations. Again, the only difference is that we have an inequality symbol in the middle instead of an equal sign. When we start to graph them, in the beginning, the process is the same, but then we have a couple extra things we have to look at the end. So to start, I'm going to treat this like y equals negative 2x plus 1. I have my y-intercept of 1. I have a slope of negative 2, so we come down 2 to the right 1, and then up 2 and back 1. But now I'm not going to connect the dots right away. This is where I have to start to look at that inequality symbol. Here we have or equal to, which if you remember from before, would have told us that we needed to use a solid or closed circle when graphing. That's because any number that worked for that inequality, if they were equal on both sides, would be included in the solution set. So that was our or equal to. If we had the open circle, that was from strictly less than or strictly greater than. So that would be like the inequality on the right here. And points where they were equal on both sides would not work for the inequality. When we graph on the coordinate plane, this is going to tell us what type of line to use. So if we have the or equal to, it means the points along that boundary line are included in our solution set, because if we look at the point 0, 1, 0 is less than or equal to negative 2 times 0 plus 1, that point would work. Whereas if we didn't have that or equal to, we wouldn't be able to include those points in our solution set. Because we want to include those points in our solution set, oh, that's wrong. This is going to be 1 on that side. I was going to say, that doesn't look quite right. 1 is less than or equal to 1, which works. Because we do want to include those points in our solution set, we're going to use a solid line when graphing. If we had something like the right-hand side here where it was strictly greater than, we would use a dotted line to show that that's where our boundary is, but we're not including those points in our solution set. So I'm going to go ahead and draw that solid boundary line on my graph. Do the best job we can here on the tablet. But now we need to remember that when we talk about inequality, it's not just that one value or that one set of values that works. You'll see that my boundary line divides my graph into two regions here. I need to figure out which of those two regions contains the points where the y-coordinate is less than or equal to negative 2 times the x-coordinate plus 1. In order to do this, I'm going to pick a point anywhere in the coordinate plane that's not on the red line to test. Usually we're going to test the origin. And if we look at our graph, we see that the origin is in what I've labeled to be region 1. This means that if I plug in 0, 0 to my inequality and I get a true statement, all the other points in the same region as the origin are also solutions, and we would shade that part of the graph to show that we want to include them. If it turns out that I plug in the origin and I get a false statement, that means that the origin and all the points on this side are not part of my solution set, and that my solutions sit on the other side of the graph. So we substitute in the origin, we say 0 is less than or equal to negative 2 times 0 plus 1, and we get 0 is less than or equal to 1, which is a true statement. So we're just going to go ahead and shade in that side of the boundary line. And now we have a complete graph of this inequality. Go ahead, pause the video, and see if you can at least get the boundary line down for the second inequality. Alright, so we've got a y-intercept of negative 3 and a slope of 2/3, so we come up 2 over 3. And if we look at our inequality, like I was talking about before, this is strictly greater than, which means that the point along this boundary line don't actually work for this inequality. So if we try our y-intercept, we would have negative 3 is greater than 2/3 times 0 minus 3. That would say that negative 3 is greater than negative 3, which isn't true. So that's why we have the dotted line here to show that we're not actually including those points. Now we want to pick a point to test, and again the origin is not on our line, so we can test that one out. And we have 0 is greater than 2/3 times 0 minus 3, or 0 is greater than negative 3, which is true. So again, we're going to shade the side of the graph that includes the origin. Your shading doesn't have to be pretty, but you just want to make sure it's very clear which side is shaded and that you don't completely cover up or go over your boundary line so that we can't see what it is. Of course we're not going to move on without looking at our special cases. The process for graphing these is exactly the same as before. Graph the boundary line and then figure out where to shade. Remember that when we have our equations x equals 3, this is a vertical line where we have all the points with an x coordinate of 3. And now we're going to take a look at our inequality symbol. We see that it is strictly less than, so this is going to be our dotted line. I can go ahead and just put in some hash marks to connect this here. And now, just like before, the last step is to pick a point that's not on the boundary line and test it to see where to shade. So again, we can use the origin, and 0 is less than 3, so that works. So we're going to shade everything on the same side as the origin. Go ahead and pause the video and try the second graph. Alright, so for this one, this is like the line y equals -2, so that's our horizontal line where all the y coordinates are -2. And because it's greater than or equal to, we have a solid line here. So we draw on our solid line, we pick a point to test. Again, we can use the origin since it's not on our boundary line, and 0 is greater than or equal to -2, so we shade everything above the line on the same side as the origin. Now, when we go to graph, our inequalities aren't always going to be given to us nice and neat in slope-intercept form. Sometimes we're going to have them in standard form. The easiest way to graph is going to be to take them and transform them into slope-intercept form. Now, because we're dealing with inequalities, there's one special thing that we have to keep in mind. Anytime we multiply or divide by a negative, we have to flip the sign. So if, as we're moving terms around and we're trying to get into slope-intercept form, if I end up multiplying or dividing on both sides by a negative value, I have to flip my inequality sign around. So if you look at our first example, in order to get y by itself, we're going to subtract 3x from both sides. So we have 2y is less than -3x plus 2. We divide by 2, and we have y is less than -3/2x plus 1. Because I didn't do any multiplying or dividing by a negative, the inequality sign stays the same. And now we go ahead and graph, just like we did before. So pause the video, see if you can graph this inequality. Alright, so we have our y-intercept of 1, our slope of -3/2, strictly less than inequality, so it's our dotted line. The origin, again, is not part of our boundary line, so we can plug in 0, 0, and that ends up being true, so we're going to shade the side with the origin. Go ahead, pause the video, convert the second inequality, and then graph it. Alright, so if we look at this one, as we move terms around, we end up having to divide by -5 on both sides, which means that we have to flip our inequality symbol from greater than or equal to less than or equal to. Then we go ahead and graph our boundary line. We have a y-intercept of -1 and a slope of 2/5. Because we have that or equal to, that's a solid line. Then the last step is to check a point. Again, we can use the origin since it's not on our boundary line. And 0 is not less than or equal to -1, so we shade the other side, that's area below the boundary line. Sometimes we're going to be asked to write an inequality given the graph, so basically backwards of what we're doing. Again, this starts out exactly the same as it would with a linear equation. We have to be very careful of the form that we're being asked to use, and we start with our slope and our y-intercept. Then we figure out the inequality symbol. So here we have a y-intercept of -1. We have a rise of 1, a run of 2, so my slope is 1/2. And if we just start with that boundary line, we would have y equals 1/2x minus 1. But now we need to figure out which way to put the inequality symbol. So I'm going to pick an easy point that is in my shaded region. So here, an easy one, since we're dealing with 1/2, let's do 4, 0. That's part of my solution, so I need to pick an inequality symbol that will work given that point. So my y-coordinate is 0, and then we have 1/2 times 4 minus 1, so 0 and 2 minus 1, and 0 and 1. 0 is less than 1, and then we look at our line, and since it's solid, we're going to use less than or equal to. So our final answer will be y is less than or equal to 1/2x minus 1. Go ahead and pause the video and try the second inequality. Alright, so for this one, again, we start with our slope and our y-intercept. We have a slope of 4, or a y-intercept of 4, a slope of -5/2. So our boundary line is y equals -5/2x plus 4. Then we pick a point in the shaded region to help us figure out the inequality symbol. So here we can use the origin. So we substitute in 0 for x and y. We end up with 0 and 4, so we know it has to be less than. And because it's dotted, it has to be strictly less than. So our final inequality is y is less than negative 5/2 x plus 4. For this question, we're doing the same thing, except instead of being asked to give our answer in slope-intercept form, we're asked for standard form. I would start the same way though. Find the inequality in slope-intercept form, then transform it into standard form, being careful that if you multiply or divide by any negatives, you have to flip the inequality symbol around. Go ahead, pause the video, and see if you can write this inequality. Alright, so if we look at this one again, we start with slope-intercept. So our y-intercept is 4, our slope is 5/4. We pick a point in the shaded region to test. We can test the origin here. We end up with 0 and 4, so we know it's less than, and then we look, we see we have a solid line, which means we need to use less than or equal to. So in slope-intercept form, we have y is less than or equal to 5/4 x plus 4. Then we have to turn that into standard form, so we subtract 5/4 x from both sides. And now we have a negative fractional lead coefficient. In order to fix this, we're going to multiply both sides by -4, and when we multiply by -4, we need to remember to flip that inequality symbol around. So our final answer is 5x minus 4y is greater than or equal to -16. For our last question, this is a pretty common one that you'll see on tests or on the SOL. They'll give you an inequality and ask you for each of a series of points whether those points are solutions to the given inequality. There are two ways that you can do this one. The first way that I'll show you is if you have a graph. So if you're given a coordinate plane and you want to graph this, just start by graphing the given inequality. So here we have a y-intercept of -3 and a slope of 3/2. So we can graph that. It's strictly less than, so this is going to be our dotted line. So we can go ahead and graph this. We want to do a good job with our graph. We want to make sure everything's accurate because this is what we're going to use to determine whether points are in our solution set. Here we can test the origin. So we want to know, is 0 less than 3/2 times 0 minus 3? And 0 is not less than -3, so we are actually going to shade the other side of the graph here. And now all we have to do is take a look at each of the given points and see if they sit in that shaded region in our solution set. So we have 3, -4. That one is pretty clearly inside our solution set. 0, 3 is far outside. 4, 3 sits on my boundary line. Now that's a dotted line, which means that these points are not included in my solution set. So 4, 3 is no good. We have -1, -3, which is close, but still not inside. 0, -4 is inside my shaded set. And 5, 0 is also inside my solution set. Now, if you don't have a graph, or if you have a point that doesn't fit within the coordinate plane that you're used, the other way that you can solve these is by substituting in your x and your y coordinates and seeing if they work. So if we wanted to check 0, -4, we'd substitute in our y coordinate and our x coordinate and see if they work. So we'd end up with -4 is less than -3, which is true. Whereas if we tried 4, 3, we would have 3 is less than 3/2 times 4 minus 3. 3 is less than 6 minus 3. 3 is less than 3. That doesn't work, so this does not belong to our solution set.